We're still talking about EIGRP, and we finished at this slide last time. So the autonomous system and process ID. The reason we're talking about those two things together is because of the misleading definition of autonomous system for EIGRP. As we mentioned before, autonomous system as a concept talks about a group of networks which are governed or controlled by a single authority, right? This is the concept. However, when it comes to autonomous system number inside the EIGRP payload, this represents what? It represents the process ID of EIGRP. So the autonomous system is a collection of networks under the same authority, and the autonomous system number is assigned by IANA, which is the entity, the international organization responsible for assigning IP addresses and system IDs to either service providers or internet backbone providers like Verizon or AT&T and so on, and institutions and so on. So one of these entities can have an autonomous system to control or to fall under the ownership of one of these entities. So in terms of EIGRP configuration, it's easy to configure a process ID. It's called the autonomous system number. However, it actually represents a process ID. So the condition is that all the routers inside a specific domain, they have to have the same process ID or autonomous system number in order for EIGRP to exchange messages back and forth within these routers. Okay, and the command is very easy, although we don't have to memorize commands. It's router. It's simply router EIGRP and the process ID. The process ID is 1, 2, 3, 4, whatever. Whatever the number is, you have to agree on this number within all these routers to allow all these routers to exchange routing update together. If the number is different, then the route updates will not be exchanged between two routers. So if those two routers, for example, one of them uses process or autonomous system number 1 and one of them uses autonomous system number 2, this technically means that for EIGRP, those are two disconnected networks. When it comes to EIGRP, they are two disconnected. They will not exchange any route updates between each other. Okay. So this is the command. So this is the command that we use, and in order for us to have this network, in order for us to have all this network to exchange route updates together and form this topology using EIGRP, then we have to have a router EIGRP 1 on each router in order to allow them to exchange route updates. So that's easy. So the function of the network command is, after we do that and we agree on router rep, remember that there is a prerequisite step that we have to do in order to trigger the route updates to go out of a specific interface or to be received by a specific interface. Right? We did that for rep, and we have to do that also for EIGRP. So the first thing is that you have to say router EIGRP 1 to indicate that the process ID for EIGRP is 1. And then this router has, for example, 2 or 3 interfaces. Then you have to run this command on each interface. which triggers or enables the route update to go back and forth on this interface. If you don't do that, then this interface will not send or receive any route updates. Okay? So for each router, you have to enable the route updates on each interface. So that's an important part. So when it comes to metric calculation, as we said before, the metric calculation for EIGRP is complicated compared to REP, and it's based on 4 major components. Okay, the bandwidth, the delay, reliability, and load. Those are 4 major parameters that we use to calculate the metric. It's a combined metric of all these parameters. So this composite metric uses weights for calculation. So we use weights K1, K2, K3, K4, K5. So we use 5 different weights. And the reason for the weights is that depending on the application, you can give more weights to, for example, bandwidth over the delay, or the other way around. Or you want to have more weight for example, the load, more than the delay and bandwidth, and so on. So this is up to the designer or the administrator to set or to configure these weights to give more precedence or more priority to a specific parameter over the other. And as we said before, the default mode for EIGRP is that K1 and K3, those are the weights for the bandwidth and delay. K1 and K3 are 1, and all other Ks, K2, K4, and K5, these are by default set to 0. So this is the default mode of EIGRP, which indicates that the default metric, so the metric is K1 times delay bandwidth plus K3 times delay. Okay? So when K1 is 1 and K3 is 1, so the metric is basically bandwidth plus delay. As simple as that. So this is the default mode. However, logically, you cannot sum bandwidth with delay. Why? Because bandwidth is, when the bandwidth increases, what does that mean? Is this something good or bad? Good, which means that, remember, the metric is a cost. Is the cost. The cost that we have to spend in order to get from one place to another, from one router to a destination network, right? So this is the cost. If the cost is high, this means that it's bad. So we have to spend more cost to get to that destination. So remember that fundamental concept. So if the delay increases, this means that, does it make sense that the cost increases? If the bandwidth increases, does that mean that the cost should increase? Cost should decrease, right? But if the delay increases, the cost will increase. So we cannot have the summation like this. Okay? So we cannot have straight summation like this. So we have to have inverse proportional relationship with the bandwidth and direct proportional relationship with the delay. And that's exactly what happens. So when we say bandwidth plus delay, we don't really mean bandwidth plus delay. As we will see in a minute, that bandwidth is calculated based on a reference bandwidth, which is 10 so the bandwidth is calculated as 10 to the power 7 divided by the bandwidth. And delay will get calculated as delay divided by 10. Okay, so that's an inversely proportional relationship, and this is a direct proportional relationship. So when we say bandwidth plus delay, that doesn't mean that it's actually bandwidth plus delay, but as we will see the details of this, that the bandwidth is calculated based on a reference delay. So we need to calculate the ratio based on a specific reference, sorry, not reference delay, I said reference bandwidth. So the reference bandwidth is 10 gigabits per second. Because the bandwidth here is in kilobits per second. Okay? So we'll see that again in a minute. But this is basically how you calculate, in the default mode, this is how you calculate the metric. So if K1 and K3 are 1, so it's basically bandwidth plus delay, but the bandwidth is calculated based on a reference specific bandwidth, which is 10 to the power 7, divided by the bandwidth in kilobits per second. Okay? So going back, the K1 and K3 are 1 and all others are 0, which means that the metric is simply K1 times bandwidth plus K3 times the delay, and the load and reliability are calculated like this. So there are two weights for reliability. So the reliability uses both K4 and K5, and the load uses weight K2. Okay, this is the non-default mode. So the administrator can set the weights for K2, K4, and K5 according to the application. And of course, as you can see, the matrix gets even more complicated, because the K2 here is multiplied by the bandwidth and divided by 256 minus the load. Okay, so it's more complicated. So we don't have to get to these complications. The default mode is enough for us. So these are the default values for the default mode. K1 is 1, K2 is 0, K3 is 1, K4 and K5 are 0. So in order to know the bandwidth on any link or to the delay, remember that bandwidth and delay are offline parameters, static parameters. These are parameters of the link itself. They are not dependent on real-time information. We mentioned that before, right? So load and reliability, they change in real time, depending on the traffic that goes back and forth on these routers. However, bandwidth and delay are static parameters, right? So in order for you to know these parameters on any interface, you can, again, we don't have to memorize the command, but it's easy, so you can use the interface command that shows you the details, and the details are basically here. So this shows the bandwidth on the interface serial 000. The bandwidth will be 1544, which is a T1 connection, which is 1.544 megabits per second. This is the default bandwidth or the common bandwidth for any T1 connection. Okay? And the delay, and again the delay here is again a static parameter or a static value that depends on the link. Okay? And the delay here happens to be 20,000 microsecond. Okay, so the delay is 20,000 microsecond, and of course the load and reliability are calculated as a fraction. So the load is calculated as a fraction of 255. Again, this is an agreed upon method to calculate the delay. So if the load, so if this fraction or if this ratio is low, this means that the link is not loaded. And that's good. This means that the cost will be low. So the load here is the load ratio is 1/255. This means that the link is loaded with a fraction of 1/255 times 100%. So I don't know if you calculate 1/255 and multiply that by 100, and this will be the percentage of how this link is loaded. Okay? So for example, if it's 255 divided by 255, this means that the link is 100% loaded. So the more that this ratio increases, the more load the link will have. Reliability is the same thing. However, when the ratio increases, this means that the network is reliable. Okay, so when this number increases, this is good. Okay, so when the reliability increases, this is something that's desirable. But when the load increases, this is not desirable. This means that the link is actually so much loaded. Okay, so that needs to be in mind. Then the way we calculate the matrix. So for example, we need to calculate the matrix in the default mode using these numbers. So in that case, it's easy to calculate the matrix as follows. So we said that bandwidth is 1,544 kilobits per second. Delay is 20,000 microsecond. So the matrix in that case, assuming K1 is 1 and assuming K3 is 1, so the matrix will be 10 to the power 7 divided by 1,544 plus 20,000 divided by 10. So this will be the matrix for this hub. Okay? And as you can see, the number is big. It's not anymore like rib. For rib, the matrix is the hub count. So it should be 1, 2. No, here, sometimes it's like hundreds of thousands. Okay? So it's straightforward. So again, the delay is a static number. Okay? It's very important to know that the delay is a static number, unlike the reliability and load, which are real-time values. It's a static number that depends on the type of the link. So, for example, if the link is 100 ATM, this means that the delay is 100 microsecond, and this is a static number, and so on. So this table gives you the common delays for a specific link type. Okay, it's a static number. Once the interface starts, it knows the type of the link, and it knows the bandwidth and the delay according to the type of that link. Okay, any questions so far? So on the other side, the metric for the reliability and the load, these are measured as real-time parameters. The reliability is defined as the likelihood that a link will fail. It's a probability that the link will fail. Okay? And of course, this is not something that's static or fixed. Okay? This is something that depends on how the network is running. And it depends on the load and some other parameters. So this is measured, as we can see here, this is measured dynamically and expressed as a fraction of 255. So the higher this fraction, the better the reliability. Okay? So if this fraction increases, this means that the network is highly reliable, which means that this is something good. On the other side, the load, again, this is a non-default value for the EIG-RP metric, and it's a number that reflects how much traffic is using this link. And again, this is a real-time information. It's dynamically calculated based on the load, based on the traffic that goes on within the system. And again, it's measured as a fraction of 255, and in that case, the higher this fraction is, the more load on this link, which means that the link is loaded, which means that the cost is higher. Okay? So these are the different parameters that we use for calculating the metric for EIG-RP. Okay, so using all these parameters, we get to a very important thing that, again, we have touched upon before, which is what we call the diffusion update algorithm. The diffusion update algorithm is another mechanism which is used to calculate the loop-free routes or the loop-free path. So the dual algorithm has 4 specific characteristics. Again, it uses the loop-free path, and it uses also the backup path. So there is, remember that backup path, these are paths that by default are not in the routing table, but these are stored in a cache in case the route in the routing table becomes unavailable. Then you get one of the backup path and put it in the routing table. Okay? This is different from, for example, like load balancing. Okay? Load balancing, you have 2 different routes to the same destination network. And both of them are concurrently valid and concurrently active. And then you send traffic 50% here, 50% there, or whatever. So you send one packet on this side and one packet on this. Backup route is different. For the backup route, you have only one route to the destination, but you keep all the backup routes in a cache. And then if the original route is not valid anymore, then you get one of the backup routes and put it in the routing table in replacement of the original route. Okay? So the dual concept or the dual mechanism, it uses loop-free path. So again, it tries to search for one route which is loop-free, and it makes sure that this is loop-free. And then it doesn't actually stop at this point. So it tries to look for all the feasible routes that are loop-free to the same destination. Okay? And it keeps all these backup routes separately from the routing table. Why? Because the main objective of the dual algorithm is to try to achieve fast conversions. Because if you remember, all the techniques that we have discussed before, whether count to infinity, a hold down timer, split horizon with pause and reverse, all these methods, they require some time. Once the change happens, once a network goes down, they require some time before they get back to the conversion state. Okay? Instead, what the dual mechanism does is to try to be proactive. by not only keeping one route to a specific destination, which is loop-free, but also it tries to keep all the possible routes to the same destination as backup routes. And we'll see how this is done from the protocol point of view, because the details on how you calculate the route as loop-free and how the algorithm works from the algorithmic point of view is out of scope. But basically, the main objective for this is to try to have fast conversion. Once a network change happens, we grab one of the backup routes and put it in the routing table in no time, rather than just setting a hold down timer and waiting for that hold down timer to expire until you get to the conversion system. No, in that case, I will keep all the backup routes. Once the network change happens, I will replace the original route with one of the backup routes which have been calculated before, and they are known to be loop-free. Okay? So based on that, the dual mechanism achieves fast conversions, and it also uses the minimum bandwidth usage with the bounded update. So it leverages the bounded update mechanism from the EIGRP to maintain the fact that the route updates when the network change happens. There will be minimum exchange of messages in order to revert to the conversion state. So that the dual mechanism defines very important terminology. Okay, so we need to understand these definitions clearly. So the first thing is what we call a successor. A successor is basically the successor for a specific destination network is basically the next hub. So remember, in the route information, we have what? We have the destination network, right? And from the with the destination network we have, this is what we call the administrative distance, which represents the precedence of EIGRP as a routing protocol compared to all other routers. If you remember, for RIP, it was 120. Okay, for EIGRP, it indicates 90, which is less than 120. This means that EIGRP has more precedence over RIP. Okay, so the lower this number is, the more precedence that this routing protocol will have compared to other routers. Okay. This is the metric. Okay. The metric with the terminology of the dual mechanism is what we call a feasible distance. Okay. And via here indicates that what comes after that is the next hub. And this is what we call the successor. So this is the successor. And this is the feasible distance. So those are those two definitions. Okay? So those are basically the two definitions. So the successor and feasible distance are not new to us. They don't actually represent to us any new information, because these have been discussed before. We used to call them the metric and the next hub. Now we call them with the terminology of the dual mechanism, the successor and feasible distance. So nothing new so far. We define what we call a feasible successor. Okay? So that's new. So what is the feasible successor mean? A feasible successor, it's a loop-free backup route to the same destination. So what does that mean? Assuming that router 2 here wants to get to the network 192.168.1.0. So what are the possible routes? Well, based on the matrix, it turns out that the cost of going through this successor or this next hub is lower, which means that the current route in the routing table will go through this, which means that this address will be the successor, and the cost of this will be the feasible distance. Okay? So this is the current successor, and this is the feasible distance. Again, the feasible distance, the way you calculate it is on this link, you know the bandwidth and you know the delay. Bandwidth is calculated based on the reference bandwidth, 10 to the power 7 divided by the bandwidth plus the delay divided by 10 for this link. And you do the same on this link, right? So the cost is the total cost on both links, which means the metric here plus the metric here. So this is the cost. That's how you calculate this feasible distance.
So the feasible successor is if this fails, goes to the feasible successor?
Yes. So the feasible successor is any other neighbor, okay, who can represent a loop-free backup route to the same destination. To the same destination. So I want to see whether instead of going this way, let's see if we can go this way and whether the dual mechanism can use this possible route as a loop-free backup route. To do that, the dual mechanism defines what we call a feasible successor. So a feasible successor, this could be a feasible successor. This could be a feasible successor. This is already a successor, so it's not a feasible successor. Okay? So let's see if this one and this one. So a feasible successor is a neighbor router which has a route to the same destination. Okay? Until now, it's logical. However, we have to fulfill what we call a feasibility condition. Okay? A feasibility condition. What does that mean? This means that this potential successor should have a reported distance to the same destination network, which is less than the feasible distance from here to the same destination. Again, feasibility condition talks about the fact that the reported distance from the feasible successor, in order to consider this one as a feasible successor, he has to report a distance to this same destination, and we have to check that this distance to the same destination is less than the distance that I have to the same destination. So someone might ask, so if the reported distance is less to the same destination, why can't I use this as a successor? Well, remember, if you have to use this as a successor, then you have to get the summation of this distance and this distance. And the summation of those two distances, they happen to be greater than the feasible distance. Okay? But the reported distance from this to the destination has to be less. Okay? Any confusion? So the reported distance from this router to this destination, it has to be less than the feasible distance from from the router to the same destination. But if you add to this reported distance the distance of this link, then it will be greater, in which case it's actually a feasible successor, but it's not a successor. It's not a successor because if we accumulate the distance between router 2 and router 1, the cost will become higher. So we cannot use it as a successor. Instead, we can possibly use it as a feasible successor. So the reported distance is a distance which R1 will report to R2, okay, about the distance to the same destination. R1 now will check. I have a feasible distance, right? I have my distance to the destination, and I have another reported distance from one of the feasible successors. Okay? So the question is, can I consider this as really a feasible successor? In order to do that, in order to check for this, then we have to have the reported distance has to be less than the feasible distance. If that's the case, then R1 will be stored as a possible backup route for the same destination. So the dual mechanism will store R1 in the cache, not in the routing table, in the cache, as a possible loop-free backup route to the same destination. So, what will happen if this situation happens? So if this situation happens, that this link goes down, in which case R2 first will have to send a triggered update to all the routers that this link has become down and so on, right? But the dual mechanism will also get triggered to check whether we have any other backup routes to this destination other than the default route, or not the default route, other than the original route. In which case, we will grab the route to R1 as another backup free or loop free backup route to the same destination. So this route will be the new route, and this will happen in no second, in no time, right? Because we have proactively calculated all the loop free backup routes before this event happens. So in order for us to do that, we have to calculate what we call the reported distance, and at R2 the reported distance has to be less than or equal to the feasible distance. If that condition is fulfilled, then R1 is considered a feasible successor to R2. If this condition is not met, then R1 will not be considered as a feasible successor. Okay? Any question? So this is what we call the feasibility condition. It's met when the neighbor's reported distance is less than the local router's feasible distance. This is what we call the feasibility condition. If that condition is met, then we consider router 1 as a feasible successor to router 2. Okay? So any questions so far before we talk about quick introduction to the link state routing protocols? Any questions so far? Okay, so this is the end of what we have categorized as distant vector routing protocols. And we said in the distant vector routing protocols, we calculate two major things, which are the distance and the direction, right? And these are calculated locally. So the route updates are collected only from the neighbors, and then you have to use the updates to calculate all the potential routes, update your routing table, and then form another route update based on collecting or gathering the information from the routing table and send it to all the neighboring routers. In the link state routing protocols, the concept is fundamentally different. Okay, the length state routing protocols, which are known as shortest path first algorithms, these algorithms are based on what we call the Dijkstra algorithm. And the Dijkstra algorithm is fundamentally different from the algorithm we use for distant vector. For distance vector routing protocols, we use an algorithm which is called حد فاكر؟ It's called Bellman-Ford algorithm. Okay, Bellman-Ford algorithm is based on a distributed mechanism which takes into consideration only local information. It takes into consideration only local information. So you get local information, you process the local information, you update your routing table, and then you broadcast or you send the processed or the result in the routing table, you send it to all your neighbors. And each router will do the same. Will collect from the neighbors only, collect information from the neighbors only. Under only there is like 100 lines from the neighboring routers only. And then you group this information, you process them, you update your routing table accordingly, and then you collect the information from the routing table and send it to your neighbors. And you have to do that repeatedly, and we said that one of the potential problems that might happen when we do that is the slow conversions. Because you have to do all these steps gradually and accumulatively until you reach to the conversions state. The length state routing protocols are based on shortest path first algorithm, which is called Dijkstra algorithm. Dijkstra algorithm is a centralized algorithm. Centralized, which means that in order for me to calculate the shortest path from one point to one point, I need to have the information on all the links involved in the source. Okay, again, so if so assuming that we have a network like this, and I need to know so any network like this, and I need to know the shortest path from this point, let's say to this point. Okay? Using link state, using the Dijkstra algorithm will run this algorithm at this point, and it needs to have the information of all these links of the entire network. It needs to have all the information about these links here, which means that it's a centralized algorithm. It takes all the information from the entire network, and then it runs one algorithm to to calculate the best path. Bellman-Ford doesn't do that. Bellman-Ford, it will get the information only from this router and this router. Okay? And then it tries to see if any of these routers have information or have best route to the destination. If not, then it waits for the information about these links to get grouped here, and then this one has to send route update to reach here, and then this one will send route updates to reach here, and so on, until this destination becomes one of the routes in the routing table of this node. Then the route update from the neighbors will have a route to the destination, in which case the route will get updated in the source. So in order to wait for this process, you have to wait for a long time, because it's distributed and based only on local information. And local information has to be accumulated gradually. For Dijkstra algorithm, the concept is different, because the information about all the links have to be in every single router. The information about all the links at time 0, they have to be in every single router. And then we calculate the route, the best route, based on a centralized algorithm called Dijkstra. فهمنا الفرق؟ Okay? So the other one is called Bellman-Ford, and this one is called Dijkstra. Someone might say that having the information about the entire network at time 0 is actually, it requires a huge amount of overhead, right? But it turns out that this will lead to much faster conversions time compared to the distance vector. Okay? So we'll stop here, and this is just a quick introduction, but we'll talk about it in details next time, inshallah.